Hi, and welcome to Unit 2 of this geography class, where we're going to talk about the U.S. and weather and climate. And specifically, we're going to be talking about Hurricane Katrina, which this is a picture of, heading slowly up this way. But we'll get there soon enough. All right, so on to first things. The changing relationship between the sun and the earth is the big variable that determines things like climate and weather and so on. We're going to start out talking about the atmosphere and the vast stretches between the sun and the earth. Now, if the sun is this little dot right in there, you go far, far away past Mercury, you go past the orbit of Venus right there, until you get to the orbit of Earth. Going all around here, not quite a circle, kind of an ellipse, meaning it's like an elongated circle. It's about 93 million miles from the sun, and only a small fraction of the sun's energy actually reaches us. This is partly because if you think of the sun as a light giving off, energy in every direction, by the time it gets this far away, 93 million miles away, only a very tiny sliver of all these beams of energy is going to be headed towards the Earth. But this is also because even though space is mostly a vacuum, there isn't much there. It's mostly totally empty. There still is a decent amount, over the vast reaches of those 93 million miles, of little specks of dust and crap like that mostly got formed, congealed into planets, came together into the big planets millions of years ago, billions of years ago rather, but some of it didn't, and some of it is still out there. And so it deflects these beams of energy. It, bounces them up, that one didn't get there either, or it blocks them, sends them back. So it makes, even that amount of energy from the sun that is directly aimed at us, a lot of it misses us, doesn't hit us. Now, when you talk about stars way out here, far, 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 far away from our solar system and from our sun, there is even a larger amount of tiny particles of dust between the different solar systems that separate us, in the area that separates our solar system from other stars and other solar systems. And there's so much dust, in fact, that the solar radiation, the energy that these stars send to us, it gets reflected off so much that these stars twinkle. And that's one way that you can always tell planets from stars, is that stars, aside from our sun, are so far away that there's so much dust between us and them that their light is twinkly. It's always being reflected off by so much dust. But planets, even though they reflect the sun's light, are close enough that there isn't that much dust to make it twinkle. There is enough to slow down that light, or to send a lot of it aside, but not enough to block so much that it twinkles. Whew. Next slide. The atmosphere is a layered mix of gases, of water vapor, and solid particles that are above, surrounding the surface of the Earth in all directions. There are a lot of different layers to the atmosphere. I'm not going to make you memorize them all, but it's important to remember that as a general rule, the atmosphere is thicker the closer you are to Earth, which makes sense because if all particles are attracted to all other particles through gravity, it makes sense that most of these atmospheric particles would be kind of held close to the center of Earth's gravity, which is in the core of the Earth. And so these particles congregate mostly down in the troposphere, the lower level, a little bit less in the stratosphere, less and less in the mesosphere, the thermosphere, and finally barely at all in the exosphere. By then you're getting very much out close to outer space. Now in the troposphere, it goes up to about 10 kilometers high, which is a little bit higher than Mount Everest, as you can see over here. But this is, even if Mount Everest isn't quite out of the troposphere, it's a little bit, it's hard to live up there. If you were to go to the top of Mount Everest, you would last for a minute or two before you passed out due to lack of oxygen, because, as mentioned, there are very few air particles up here. And after that, it would be so cold that you would pretty much freeze to death. Yeah, too bad. That's why you shouldn't go to Mount Everest. Stay at home. That's what your mother thinks anyway. The atmosphere is important for a lot of reasons. One of the reasons is that it traps heat on the Earth, which is, it can be a good thing, it can be a bad thing. In general, though, and this is called the greenhouse effect, it's a good thing. You have, if we're going to divide up the solar radiation that comes from the sun, some of it, as it comes here, we're going to start out. This slide says 20% is scattered, deflected by clouds, a little bit before that even by the atmosphere. So only a certain amount even gets through that kind of first layer or two. A little more is absorbed by clouds and atmosphere and by Earth. And now when the solar radiation, which you can see as light, and you can also feel as heat, if you go out on a sunny day or something, you put your arm in the sun, you'll feel heat. When it's absorbed by the Earth, well, that's the heat that you feel. When solid things, when matter absorbs that solar radiation, it creates heat. And the heat then kind of diffuses out. It changes its state from this light, the solar radiation, to infrared heat. Like if you've ever watched the Predator movies, you think of Predator vision. It sees creatures by their heat signals. It sees them as like red and green and purple shapes moving around in the jungle or somewhere. That is basically what solar radiation turns into when it's absorbed by things and it becomes heat. Now, that kind of infrared heat it doesn't shine out necessarily like solar radiation. It kind of spreads in all directions. So the Earth, once it absorbs the light, it's re-emitted as heat. And it goes somewhere out there back into the atmosphere. The thing is, though, go to the next slide here, our atmosphere, again, because it's all these little dots and particles and that kind of thing, these particles then absorb the heat that's radiated from the Earth. And then these particles start vibrating very quickly on the molecular level, which is what heat basically is. It's molecular vibration. And then that heat from there spreads out in different directions. So some of this heat can eventually escape back out into into outer space, but the more particles you have here in the atmosphere, the longer the heat is going to stick around, meaning the hotter the atmosphere is going to be. Now that's really, like I said, it's kind of a good thing in the long run. Without the greenhouse effect, the planet looks like, say, Mars, which is freezing cold. It doesn't really have an atmosphere. It can't keep the sun's heat. The sun's solar radiation comes to Mars, hits Mars, either bounces right back off, or once it hits Mars, it just radiates out in infrared, and there's nothing to stop it. So greenhouse effect has a bad rap to some extent, but it is necessary for life on the planet. So we will be coming back to this a little more in the future. That is all of this first set of notes.